All right, let's give this a shot. Max, I hope you're feeling better. All right, so here's what we've got today. We're going to go through interacting objects, one of the hardest things to really understand, okay, about how we solve problems that have two bodies interacting with each other. Now, to begin, we're going to review Newton's third law. Newton's third law says that for every action, there's an equal and opposite reaction. Now, if you remember, the key to understanding and working with Newton's third law is the idea that these forces act on different objects. If I push on the desk pushes back on me. Those are equal and opposite forces, right? Everybody agree? So they're action-reaction. However, when we were doing problems up to now, we haven't really worried about action-reaction because we've drawn a box and we've drawn the forces acting on the box. And we may have lots of forces acting on a box. You may, in a box problem, you may have a force this way and a force this way and the weight and the normal force. You got all these forces acting, but how do I know that none of those are action-reaction? They all act on the same object. And remember, action-reaction forces have to act on different objects. That's not to say that we won't encounter problems where we need to concern ourselves with action-reaction forces. For example, take a look at this problem. You have a hand pushing on object A, block A, which is connected to block B. It's like there's a surface there, a small block and a big block. And collectively, they're accelerating to the right. Everybody got it? Now, this is a really important thing to understand, is that if you want to analyze block A's motion, how it moves, we're only interested in the forces that act on block A. If we want to see how block B moves, we would only be interested in the forces acting on block B. Everybody got that? Now, what forces are acting on block A? Okay, first let's get the ones that, we're going to say this is a frictionless surface. But you're right, there's weight of A and there's normal force. But those are up and down, they cancel and they don't matter, right? Because there's no friction. So really, we're only looking at horizontal forces. And you're right, the hand is pushing to the right on block A. Is that the only force on block A? No, what else? B pushes back. There's a contact force of the force of B pushing back on A. Everybody agree? Which one of those is bigger? Do we know is bigger? The hand force to the right or the contact force of B back to the left?
The hand.
How do you know the hand, Jake, is
It's
bigger?
accelerating to the right.
Absolutely. This system, these blocks are accelerating to the right. That must mean there must be a net force to the right on that block. Let's talk about the forces on B. What forces act on block B? You do. You have the weight of B and the normal force. But again, we don't really care about those. Those are going to add up to zero because it's not going to start hovering or going up and down. So what about the horizontal direction? It's the force of A on B. Please note that block B does not feel the hand. Now, that's something that's important that we need to say. It seems obvious, but sometimes we misunderstand. I'll give you an example. You're standing in line in the cafeteria, and the person behind you bumps into you, pushes you forward. And you turn around like anybody, and you say, hey, why'd you bump me? And guess what they say? It wasn't me, it was the person behind me bumped me, right? Kind of like a chain reaction at an intersection. One car hits another, right? So here's the deal. Block B doesn't even know the hand exists. I know I'm kind of assigning a human quality to block A like it has, or block B like it has a conscious. My point is, it doesn't feel the hand. It only feels A on it, right? And we already said, what about the force of B on A compared to the hand force? It's less. So that reaction force of force A on B is also less than the hand. Does that make sense?
Yes.
And together, these start moving to the right. But the only force on this is from this block. Everybody good? These forces of A on B and B on A are what we call contact forces. And one way we'll often write that is we'll say the force on A, or force of A on B, equals the negative force of B on A. And these are action-reaction forces. They act on different objects. They're equal and they're opposite, and they act on different objects. Everybody okay with that? In this case, we sometimes will just refer to it as the contact force C. All right, so we have the contact force between those two blocks. Everybody good? Okay. They're going to give you some detailed steps in the book on how to approach these problems. And then I'm going to do them slightly different. In fact, here's what's going to be interesting. They're going to do a problem like this. I'm going to give you different numbers because I want to make it easier, okay? No, I'll use these same numbers. 3 newtons of force with the hand. This block has a mass of 5, and this block has a mass of 10. So I'm going to do this problem, but I want to show you that the book ends up doing it in the slides. They do it a little different than I'm going to do it to get an answer, all right? So I want to do this problem on paper and pencil up here, and you ought to copy down what I do, okay? So let's draw this problem very, very specifically. First of all, let's remember we've got a 5, a 10, and a hand that's pushing with what? 3 newtons. All right. So let's go ahead and do this. Okay. We're going to call this interacting objects. And in interacting objects, I've got, what did we say the masses were?
5 and 10.
5 and 10. Call this A, this B. So the mass of A is 5 kilograms. The mass of B is 10 kilograms. And we have a force that's how much? 3 newtons. Now I've got 5 and 10 and 3. We'll assume they have more significant figures. Okay? So how do we find out a couple things? What we're typically interested is in the answers to 2 questions. Number 1, what is acceleration? And number 2, what is the contact force? That's what we're going to be interested in here. What is the acceleration and what is the contact force between the blocks? Now, just like we've done in every kind of problem like this before, what do we do, Mr. Pappas? What do we need to do on this one? Are you with me there?
Yeah.
All right. How do we solve these problems? We've been doing these for a few days. What do you draw? What do you do first?
The force diagram.
Yeah, what do we call that? A what? Free body diagram. So we're going to draw separate, so spell separate, S-E-P, separate or separate? Thank you. Separate FBDs. That's why I teach physics and not English. All right, so we're going to draw these boxes separately. All right? There's A, and way over here, we'll put B. I'm going to put a dot in the middle because we're going to draw our free body diagrams. All right. What about block A? What do you want to draw? What forces are acting on block A? Anybody?
Force from the hand.
We have the force. Now, we could draw the weights. Wouldn't you agree? Do I need to really draw those?
No.
What is the weight of this block? Let G be 10. 50 newtons down, but what's the normal force? 50 newtons. And by the way, this is frictionless. So we don't even need to really worry about the weight. So yeah, let's just draw this one. I'm going to draw it 3 long. I'm going to draw it 3 long. Yeah. 3 newtons is F. Is that the only force acting on this? No. What else acts on it? B on A. So we're going to, how big do I make it? No, if it were the same, then that force would be what? 0. So this is the force of B on A. Everybody agree? What about this block? What forces act on it?
A on B.
Yes, how big do I make it?
Big.
No,
The same.
the same in size as this one. So again, F of B on A equals negative F of A on B. As we said, they are action, reaction. And these are the what? These are the contact force. Now it's important to understand, whatever we find these to be, they're going to be less than 3. We don't then add them up. We don't like, if this is 2 and this is 2, we don't add them up and say, oh, the contact force is 4. No. This is the contact force on this block. If it's 2, that's the contact force. Now, so there's our separate free body diagrams, right? We can then draw we can then, for example, do a net force equation for each. All right? However, we're going to do this. We're going to treat the system of blocks as one big block. What would the mass of that big block be? 15 kilograms. So we're going to do that. And now we're going to use Newton's second law. A equals what? What's acceleration in Newton's second law? A equals what? Net force over mass, right? We did a whole lab with that. Acceleration is net force over mass. What is the net force acting on these blocks if you look at them collectively? 3 newtons. Wait a second. What about the contact forces we just spent time drawing? They cancel. If you look at it as a whole, this force and this force are equal and opposite, act on different objects and they act in different directions. They cancel with each other. Everybody okay? But what mass is the total mass? 15 kilograms. What do we get? Somebody with a calculator do that for me. 0.2 meters per second squared. So I found the acceleration by treating them as one big system. Now, why can't I find the contact force in a simple way like this? Why can't I look at them as one big system and find the contact force? What happened to the contact force when I just viewed it as a big block of 15 and 3? What happens to that contact force? It like disappears. We don't even worry about it, right? So to find the contact force, we're going to look at just one block. Which block do you want to look at?
A.
Why?
I don't know. It's just smaller.
My advice is to always look at the block that has the least number of forces on it.
So B.
It would be B. You can do it with A. You're absolutely right, Jerry. You can do it. But I'm going to do it just looking at B. So we're going to go block B. All right, so we're looking at block B. What is the net force on block B? What force is acting on block B? Anybody? Now just look at the picture. Tell me what it's called. Yeah, the F of AB, which is our what? Contact force, right? What's net force always equal to? MA equals our contact force. What is the mass of that block? 10 kilograms. What's the acceleration of that block? Do we understand why it's 0.2? The blocks are together. They're both accelerating the same. 10 times 0.2 equals our contact force. What is 10 times 0.2? 2 newtons equals the contact force. That's the net force on block B. Now, Jerry is right. We should be able to do this for the other block. What's the net force on block A? We should do it for this and get the same answer. What's the net force on block A? 3 minus the, which is, what are we calling that? 3 newtons minus the contact force, right? What's net force equal to? MA, what's the mass of that block? 5 kilograms. What's the acceleration? 0.2. What's 5 times 0.2? 5 times 0.2. 1 Newton equals 3 newtons minus C. What does C equal?
2.
2 newtons. That's the contact force. Is everybody okay with how we did this? The key is sometimes it's beneficial to look at it as a what? A system, one big block. But then when you want to look at the contact force between them, you want to look at what? Individually. Look at the box individually. Everybody got it? Not too crazy. So that contact force between those blocks is 2 newtons. All right, let's go on. Now that you've seen that. Like I said, If you want to see another way to work this, I think it's a little more complicated, but they do it in these steps here. They talk about separating it. Look, they draw the free body diagram on each, right? They call it the force of the hand. I called it, that was the 3. There's B on A, there's A on B, right? Okay? So they kind of walk through how to do that. And they get, what do they get for the contact force? 2 newtons. All right, let's look at this problem. We're going to throw you into the deep end of the pool here. This is actually a problem on an AP Physics C exam from about 5 years ago. All right. Oh, by the way, look outside. We've got a little wintry wonderland going on. A little nice gentle snowfall. It's kind of nice. All right.
Get after sea lunch.
So I don't think so. Keep dreaming that value. All right. Consider the situation in the figure. This has a lot of moving parts, a lot of things to consider. Which pair of forces is an action-reaction pair? Now let me remind you, or you remind me, what constitutes an action-reaction pair? They have to be what?
Separate.
Equal. They have to be opposite, and they have to act on different objects. So we want to find out what are the action-reaction pairs. But what I've decided on this one is it's almost too much to throw at you. So we're going to draw the free body diagram for this problem. You guys are going to help me draw the free body diagram for this problem. All right? So we're pulling on that bottom block, and it's pulling out from under this. This one's not moving. Do we understand why this one's not moving? It's got a rope. Okay? Now, next thing, they tell us that this surface right here is frictionless. But this surface is not. How would you create this in the real world? What might we make this bottom surface?
Ice.
Ice. And yet these are 2 wooden blocks against each other. Everybody got it? And we're pulling this out from under. So, we're going to use our dot, our particle method. I'm going to move these a little bit away from each other so they don't interfere. And let's draw the forces acting on each block. What do we got? And by the way, I believe this top one we call A, and this one's B. All right, so somebody start giving me forces.
Weight.
Weight of what?
Top block.
Top, you want to do the weight of the top block, okay? So let's do that. That's the weight of A. What else do we have?
Normal.
The normal on that block, right? Everybody agree? Everybody okay with those being equal in size?
Yeah.
What about the bottom block? What forces are acting on it? Its weight. It's a bigger block, so I'm going to make its weight a little bigger. Is that the only thing acting down on that block?
No.
No, we have.
The weight of A. The weight of A.
That's really the force of A on B, which is the weight of A, I will agree. That and that are the same size. This has its own weight, but that's pushing down on this. Everybody agree? What else acts on that block then? How big is this normal force?
Or no, it's
Both of those, yeah.
It's both of those. Do we understand?
Yeah.
So we're going to draw a normal force that's pretty doggone big. That's the normal force on that one. So we have the normal force on A, and this is the normal force on B. And it's equal to what, if we want to draw it out? The weight of B plus the weight of A. Everybody agree with me? Now's where it gets tricky. What else do we have acting?
the force of you pulling.
You pulling, right? Let's do that. That's the force applied, that F, that 20 newtons. Everybody got it? Is that the only force that block feels?
The tension or
Friction.
the friction.
It feels friction. Not this friction, but it feels friction there. Which way do you think that acts?
That way.
Yeah, everybody sees that, right? It's the other way. It's back the other way. And is it bigger or smaller than this?
Smaller.
Smaller. We'll make it about like that. That's F, K, kinetic friction. We know it's smaller because what's this block doing? Accelerating to the right. So this F is bigger than FK. So we've got that block done. Are we done with the top block though? Yeah, Jerry, you had a question?
Yeah, but isn't the bottom a frictional surface?
It is. I'm not giving you the friction between these two. That's zero.
Yeah.
But we're pulling it out from under, and so there's friction there. We have to overcome that,
Yeah.
right? What about the top block? What else is acting on the top block? There is a tension back the other way, right? How big do I make that? Well, if there were no rope, what might happen with this block?
It would just,
It would start, if we took that away, it would start pulling with this, right?
yeah.
What's keeping it from just staying there as we pull this? No. If there's no rope,
Oh.
it would be friction, right?
Oh.
So this is the tricky one. On this block right here, there is a friction force. Now that's the friction force by this one acting on this. Okay, do you follow that? Now that seems weird because you're going, wait a second. Friction always opposes the sliding motion. Well, it does. The sliding motion it's trying to slide this way. In other words, if I just did this and said, we're pulling this block this way, which way would you say friction acts on that block? Back and to the right. Do you see how that's really what's going on? Now I know we're not pulling this block this way, but it's like we are because this block's going this way. So it's like we're pulling it. Remember, frame of reference you can change. And if you look at the frame of references, if we just zoomed in on this, it would look like this block is being slid to the left. So there's a friction force to the right on that. And so how big is tension?
Bigger than that.
Now wait, does this block go anywhere? So how big is tension? Same as that, yes. So that's really kind of tricky. Now, I'm not going to ask you to work this problem. You could do it. You could find all kinds of things. You could find the force of friction. You could find the tension in the rope. That's what they had you do in AP Physics C about 5 years ago. But I just want you to tell me, of all those forces, which ones are action-reaction? Let's review. They have to be equal, they have to be opposite, and they have to act on different objects, right? So is it A, the tension of the string and the friction force acting on A? What do you think? Think those are action-reaction? Why not? What criteria don't they meet?
Different object.
Yeah, they act on the same object. How about B? The normal force on A due to B. So that normal force right there on A due to B, this block pushing up on that. And the weight of A. Why not?
They're not equal.
Same object. C, the normal force on A due to B. The normal force on A due to B, that same one. And the weight of B.
No,
No, they act on different objects, but
not equal.
they're not equal. How about the friction force on A, that, and the friction force on B? They are.
Yeah.
Those are the actions. Just take your hand and go like that. Wouldn't you agree whatever force was imparted to this was also imparted to this, but they were what to each other? Equal and opposite. Everybody good? So our answer to this one is D. Everybody good with this? Kind of a tricky one. Yes, Matt?
So it's equal act on the, different
Action reaction are equal, opposite, and they act on different objects. All right? So that's a tough problem. It's doable, but it's a little beyond what we're going to cover in this class. Let's do some questions now and see if you are getting this. Some clicker questions. Boxes A and B are sliding to the right on a frictionless surface. Hand H is slowing them, is slowing them. So these are moving, and you're slowing them down as they slide. Box A has a larger mass than box B, considering only the horizontal forces. So we're not worried about the weights. All right, frictionless surface. We're just slowing these down. They're already moving. We put our hand up to kind of slow them down. All right? Is force B on H, B on the hand, equal to the force of hand on the B, equal to the force of A on B, equal to the force of B on A? Are all the forces, the hand on the B on the hand, the B on the A on the B, are they all equal?
No.
Or is it something else? Everybody agree it's not going to be A. By the way, is this okay though?
Yes.
And is this okay? Yes, because these are what to each other? And these are equal and opposite action reaction. It's this side. So let me give you a second to look at this and see if you can figure out which one is going to be right. You ready? 3, 2, 1. What do you got? Hey, good deal. You guys are figuring this out. Absolutely. Remember, your hand has to stop everything. The force of B on A only has to stop what? A. So it can be a smaller force. Okay? It's that contact force. Let's go on. Let's talk about ropes and pulleys. Ropes and pulleys. When we pull a box with a rope, pull a box with a rope. We did this the other day, and you saw Brian Jones do this. When I do this, pull a rope like that, okay? The box is pulled by the rope, so the box's free body diagram shows tension force. There we go. We just have tension. That's all. The rope has my force forward and the force of the box on the rope. Right? I mean, look at the rope. If you want to draw the force on the rope, what is the rope feeling? My hand pulling this way and the box pulling back the other way, right? The box only feels what?
The rope.
The rope. Everybody good? But the string is massless. We're assuming strings are massless. So the mass of the rope is 0. So if we look at Newton's second law for the rope, we get net force, the force box of the rope, is, we have the force minus the tension, the force box of the rope, all right, is mass times A. We get 0. So there's no, the net force on the rope is 0. Here's the key to this. What this implies is that when you have a rope, the tension is the force that the rope exerts on the bus. Tension and the vector are in the action-reaction pair and of the same magnitude. This and this are equal. Now I know what you're saying. How can the rope be moving? We're not saying the rope isn't moving. We're saying that these two are equal, all right? Because the mass of the rope is 0. Got it? So what's, if net force equals MA and M is 0, what's net force have to be?
0.
0. Does that mean acceleration has to be 0? No. So I could be doing this and accelerating. There's acceleration of the rope, but because the rope is assumed to be massless, then the tension on the rope is the same everywhere. All this is to say that important fact, that when you have a single rope, the tension everywhere on the rope is the same. So yes, whatever force I pull with and with my hand is going to be the force pulling on the block. Everybody got it? So if I pull with 100 newtons, that's the force pulling on the block, 100 newtons. Okay? Generally, the tension in a massless string or rope equals the magnitude of the force pulling on the end of the rope. All right? The tension in a massless string or rope is the same from one end to the other. Whatever, if I have a rope, doesn't matter what it's doing, the tension everywhere on that rope is exactly the same. Okay? Please note that I don't add these up to get the tension in the rope. The tension in the rope is one of those, is either one of them. All right, take a look at this. Boxes A and B are being pulled to the right on a frictionless surface. The boxes are speeding up, so we have acceleration this way, all right? Box A has a larger mass than box B. How do the tension forces of these ropes compare? First of all, are these the same rope? No, so their forces don't necessarily have to be the same. So take a look. Do you think tension 1 is greater than tension 2? Do you think the tensions on each rope are the same? Or do you think 1 is less than tension 2? Or do you think we just don't have enough information to figure this one out? Take a moment to think about that. Three, 2, 1. What do you think? A little bit all over the board on this one. It is 3. Let's take a look at why. This rope has to pull what? All of it. This one only has to pull what?
A.
If I had asked that question this way, take a look. If I had gone, hold on. Which one of those ropes clearly is going to experience more force?
1.
Obviously, this one's holding up both of them. This one's only holding up the right. Everybody agree? Same thing. All we've done is turn it sideways and accelerate it. Got it? All right. Hey, have a great day, and we'll do lab tomorrow. 30 minutes.